All right, what's up, everybody? Welcome. How are we doing with the live crew? The 2 live crew, right? Anybody, we need more time? Okay, need a little bit more time? All right, well, I'll just talk to everybody in the crowd for a minute while we're getting some more time together. So we're going to be live streaming this out to the whole world. Everyone in the world is going to watch this. And to facilitate that, we have this amazing crew here who's going to help us with this, and they're just finishing setting up because there was a little bit of a mix-up with the room. It wasn't clear which room we were supposed to be in. So if you see these guys walking around, they're gonna. What does Frank Zappa say? They're gonna stay out of your way, and they're just gonna let you enjoy the show, something like that. You guys ever seen that concert? It's like 1981. You guys were all there, right? I think I was 1 year old when that concert happened. It's a good concert. All right, so we're not quite starting yet, so, but I'll take some questions. If you guys have any questions, we'll just start out backwards, right? I guess I should open up the PowerPoint. That probably makes sense. You guys like PowerPoint? I love it. What's the longest PowerPoint anybody sat in this weekend so far? Pretty good, that's pretty good. Yeah, can anyone top that? Yeah. All right, so this session description that was posted here, it basically says that the intended audience is for beginners and intermediates. So if anybody out here is an expert and you want to scooch over to another room, I won't have my feelings hurt, okay? Does anybody have any questions about, oh, you know what, this is perfect. I made this PowerPoint too long and ended up putting in some kind of bonus material down here at the end. So these are some quick tips that I learned when I was going through the world of sheet metal. So I think what we're going to do is we're going to start out with these quick tips, and then we'll get into the official presentation. Now, the only thing I'm worried about is, what's our ETA? Oh, sorry, I'm putting him under pressure. Hey, Bill, hey, Steve, hey, Pat. How much more time do you think we're going to need? 2 more minutes, you got it. All right, perfect. That's exactly how long these tips are, so we are right in sync. This is perfect. So one of the things that you learn when you're going through the wonderful world of sheet metal is that you can create what's called a miter flange. And a miter flange is a really cool tool that falls into the category that we're going to discuss today called base flange and friends. And so when it comes to the miter flange command, what you do basically is you select an edge and you use that edge to create the miter flange profile sketch. All right, so what do I mean by that? Well, the miter flange is a sweep. So imagine we were going to take a sweep and create a sweep that goes up here like this, around like this, and then down like this. So where is the sweep profile going to be? The sweep profile is going to be like right here. Let's say we're going to create a sweep profile that looks like that. Can everybody see that in the back? You guys all see it? So now we need to create a plane at that location, right? So what I'm going to do is I'm going to select this edge for the miter flange. So I'm going to start the miter flange command, and then I'm going to click on this edge. Now, where I click it, if I click it at this region, or if I click it in this region, matters. I'm going to click it in this region. And so Solidworks automatically creates a new plane normal to that edge at the endpoint and puts me into sketch mode on that plane. And now I'm going to begin sketching and create the miter flange, which is something that we'll talk about this a little bit when we get into the class about this idea of miter flange. This is like the pre-game warm-up, okay? If you guys are walking in, you haven't missed anything. Jose, what's up? How you doing? Welcome. Haven't missed anything. We're just getting warmed up here. But you can see here that I can go into miter flange and I can rip that miter flange around, right? It's pretty cool. So this got me thinking when I first went through this process, does that work everywhere in SolidWorks? Like, for example, if I had a boss extrusion and I wanted to begin a new sketch normal to an edge at an endpoint. So let's say, for example, this boss extrusion has some draft on it. So I'll just say I want this to be drafted out 6 degrees. And now I want to create a new plane normal to this edge at an endpoint. Well, I can click on this edge, and I can go to Sketch, and then I can click the Sketch command, and it actually creates a new plane normal to that edge at the endpoint. Kind of cool, right, that it happens like that when you're in solid mode and you're picking on a solid edge, but not actually that practical. It doesn't come up that often. But what does come up quite often is the ability to do that off of a curve. So if you have a helix spiral, or if you have a composite curve where you've joined multiple curves together, you can actually just pick this curve here and then pick reference geometry plane, and it will create a new plane normal to that curve at the endpoint. I don't know why I didn't do it, because I'm doing it live, right? Curve. Nope, reference geometry plane, and it'll do it. It will do it, yeah, normal to that endpoint. So there are some other spots where you can use that, and this was kind of a quick session that I was going to originally include, and then I decided not to include it because I wasn't sure we were going to have enough time. But thanks to this awesome live crew, they gave us this extra little bit of time, so now we get to show you these extra little tips. Now, although that one's kind of cool, but not that amazing, this one is totally amazing, and it's one that has helped me so much. I use this all the time whenever I am working in Solidworks. So convert entities creates a soft relationship. Show of hands, does anybody know what I mean by that? Like, maybe you've never heard that term, but do you know kind of what I mean by that? Nate, one other person back there? Okay, so like 3 people, now there's more hands going up. Everybody wants to join now that you did it. It just took one person. So what this means here, this soft relationship idea, is that when you're working with the convert entities command, I mean, first of all, let's talk about the edge flange. So I'm going to click edge flange here, sheet metal, edge flange. And what we get with the edge flange command is a new flange that exists along this entire edge. And we can get in here and we can edit this flange profile. It's a sketch. And you'll notice that this end of the sketch here is black, and this end of the sketch here is black. And that's because this relationship here is a convert entities relationship. So this lower edge of this rectangle has been converted off of the existing edge of the model. But when we're in edge flange, we can just grab this line and move it over. We can just grab this line and move it over. How is that possible if it was black? If it's black, doesn't that mean it's constrained, right? And you shouldn't be able just to grab it and move it like that. This is the only place I've seen in SolidWorks where this kind of like sticky relationship or soft relationship exists. And it comes in the form of convert entities. And you can demonstrate this, and you can see this really well if you just make a couple of circles and extrude them. So you can see that I've got a circle here that's horizontal to the origin, a circle here that's horizontal to the origin, and I'm going to say extrude. And then what I'm going to do is go to the front plane and pick this edge here, and I'm going to say convert entities. And I'll pick this edge here, and I'll say convert entities as well. Just to make sure that that sketch is a little easier to see, I'm going to go into sketch color and say I want that to be red. So now I'm going to edit this sketch of the circles, and I'm going to make this circle smaller and this circle larger. And what's going to happen to those lines? They're going to move, as expected, right? But this is a convert entities command, so the endpoint of this line has this kind of soft relationship. So I can actually grab this endpoint and just move it over, and now it's no longer going to stick to that convert relationship. Now, I've never seen this anywhere else in SolidWorks. I don't know if you guys have, feel free to yell out. But I've never seen this kind of like I said, I call it like a sticky relationship or a soft relationship. And I only learned about it because of sheet metal. I was going through sheet metal and I was like, hey, how come edge flange, how come the sketch is all black, it's fully constrained, but it can still be moved? You can still grab the edge flange and move it over, make it smaller, make it larger. And I learned that that kind of soft relationship exists all throughout convert entities. So practical application of that might be something like you are going to create a new rectangular boss extrusion, and then you just want to cut a notch into a corner of that. So you do sketch, convert entities, so now the whole thing is converted. And now I'm going to delete this convert entities because this is kind of like collinear. So I'm going to delete that one, but the line is still black. But I can just take this now and move it over. And now the line's blue. And now I can just add a dimension, make that a little bit smaller. So even though it shows up as black, sometimes you actually still can grab that geometry and move it. It's still predictable, which I'm sure you all remember from the song. Fully defined means that it is predictable, which is what we want. But it's got this kind of soft relationship, so you can turn it into underdefined. Cool? Any questions? So far, so good? We're good? Pat? Right? All right. Everything sounds good. He's giving me the thumbs up. So I think we're good to go here. Welcome, everyone. Let me get the official welcome going here. All right, let's go back to the beginning. Not thank you. Start. Beginning. Okay. All right, let's give it up for Pat and the SolidWorks Live team. Good job, you guys. This is going out to all over the world, so thank you guys so much for coming in and giving us this support to make this a little bit of a kind of a new experiment in the world of conferences and technical sessions. We're going to do sheet metal tips and tricks, and as I mentioned earlier and in the description, the goal is for this to be for beginner and intermediate users. So let me find out a little bit about who you are. So how many people in the room are newbies? So maybe you're just getting started with Solidworks, maybe you're just getting started with sheet metal, maybe you really haven't done too much, feel a little lost. Okay, good, awesome. You guys are in the right place, welcome. How many people would consider themselves kind of intermediates when it comes to sheet metal? So you may work with sheet metal for a few years, but you're trying to learn a little bit more of the ins and outs of what's going on in the world of sheet metal. Okay, great. So you guys are in the right spot as well. And is anybody in here an expert, a sheet metal expert, certified sheet metal expert? I don't know if there actually is an expert certification, but okay, good. A few of you are in here. So you guys probably aren't going to learn too much about sheet metal, but I'm pretty sure you're going to learn about some other things. Like maybe you just learned about convert entities being a soft relationship. Maybe you didn't know that before. So my name is Toby. I'm a certified SolidWorks expert. I started doing tech support and training in 2001. I've taught a lot of sheet metal classes. I also work with sheet metal in the field for a few years, so I have a little bit of practical experience that I draw upon as well. I also have a ton of content posted on YouTube, so if you want to check me out on social, that's a good place to find me. You can just do a search for Toby Solidworks. You'll probably find my content. I've got a lot of videos up there. And I also have, just this year, created a new kind of a new handle online, and you'll find me on YouTube and Reddit as Too Tall Toby. Too Tall Toby. This is the first time I'm announcing it, so I hope that you guys will get out there and check it out, and check me out on YouTube. I think I have 2 subscribers. It's probably me and my wife, and probably just because she felt bad, you know. And so you guys can check me out there, Too Tall Toby. Sorry, you guys, I already had that joke pre-cooked before I saw you guys yesterday. These guys actually subscribed as well. Okay, so let's look at the agenda here. We're going to talk about what's going on with how we create sheet metal models. We're going to talk about how we go from having a sheet metal model to having a flat pattern, and then we're going to finish up with some audience questions. We only have an hour together, so it's going to go by pretty quick, but I'm sure that you're going to get a lot out of it. What I hope that you get out of it is that at the end, you understand the different ways to approach sheet metal and the different circumstances that might make one way a better solution, right? If there's 3 different ways to get started with sheet metal, which one should I use? Hopefully by the end of this presentation, you'll be able to answer that question. I also hope that you're going to be able to understand the best way to create a flat pattern. Might seem like a straightforward process, but I think you may be a little surprised. And I hope that you learn at least one additional tip or trick by the end of the presentation. Does that sound good to everybody? Everybody sound like they're in the right place? Okay, I'm seeing some heads nodding. Awesome. All right, thank you. One last thing I just want to say is, along the way, if you have any questions, just either raise your hand or just shout it out. I am happy to deviate a little bit from the lesson and address any questions you have. I am here for you. I want you to get the most you can out of this training. And chances are, if you have a question, somebody else in the room has the same question. So you're helping everybody, right? It's a community. Let's get into the first section called the 3 different methods of getting started with sheet metal. And we're going to start out with the first method, insert bends. This is a method that actually came out a long time ago, almost immediately after SolidWorks was released. SolidWorks came out in 1995, and this functionality was added in 97, 98, right around that time. So very old bit of functionality, not used too often these days, but there are some spots where this can be very useful. The way that insert bends works is that you would actually start out with a solid model. This is how we used to have to model sheet metal. We would go through, we create extrusions and cuts. We'd have to ensure that all of our walls were the same thickness. It's what we call uniform wall thickness. If we did not achieve that, then our models wouldn't be able to be flattened. And after we created that model, we would launch a command, and that command was called insert bends. It actually came from the pull-down menus back then. So you go into insert bends. You would then be able to declare what your fixed face is, along with a couple of other options. And then finally, you would have your completed sheet metal design. You'd be able to flatten it. So let's take a look at what this workflow looks like in the SolidWorks software. So we can see here that we're going to start a new model. This model is going to be in inches. And we're going to go to the front plane and begin a sketch. And we're going to begin a new sketch here. Make a rectangle. I'll say it's 2 inches high by 5 inches wide. And I'm going to make another rectangle here. Let's say this one is 0.75 by 2 inches. And I'll just drag that down to the corner. And then I'm going to use the boss extrude command. I'll pick this contour here, and I'll bring that out to, say, I don't know, 3 inches. Good. Now I'm going to go to the shell command, and I'm going to say that I want to shell this thing to a wall thickness. Computer, magnify. Okay, there we go. So what do you guys think this wall thickness should be? I don't know, let's make it say 90 thou. Okay, now we're doing this with a shell command. We're not doing this with a traditional sheet metal command. We're doing it with a shell command, computer demagnify. So we're going to make this here 90 thou, and then we're going to pick these faces here to remove, and we hit the green check mark. So now we have accomplished the first step. We've worked with our traditional solid modeling tools. We've created a solid model with uniform wall thickness. We're ready to go to the sheet metal commands. So we turn on our tab for sheet metal, and we go to the command insert bends. It's an old command. It's been in the software for a long time, insert bends. And Solidworks says, which face do you want to be fixed? This is kind of a marginal decision. It doesn't really matter. It's sometimes in downstream commands, it makes things a little bit more intuitive. Like, for example, I probably wouldn't pick this face. I would probably pick this face or maybe this underside face here as my fixed face. It basically just means that face is going to stay still while everything else unfolds. But that second statement, while everything else unfolds, is going to be problematic because if we examine this region back here, this back panel, it's not going to be able to unfold because of how this edge is fused together here. So I have to tell the software that that edge should no longer be fused together. And the same thing with this edge here, and this edge across here, and this edge up here. And then this back panel is going to be able to kind of lay down like so. So I'm going to tell the software that that is the scenario by utilizing what's called the rip parameters command. So with the rip parameters, we're able to say this edge is supposed to be ripped. So I'm going to just open up that edge. This edge is going to be opened up. This edge is going to be opened up. And this edge is going to be opened up. The final input that we need to establish when we're working with sheet metal is what is the default bend radius? What's going to happen in these corners when I go to bend the sheet metal? So first we declare what the wall thickness is. We actually did that earlier in the model. Now we declare what the default bend radius. Now if the wall thickness is 0.090, what should the default bend radius be? Or for all my sheet metal homies in the room, what should it not be? What do you think? Right. It should not be less than the wall thickness. So if you're brand new to sheet metal, this is a fundamental rule of sheet metal. You don't want to make the bend radius less than the wall thickness. If you do, you're going to end up having problems. You may break the parts, you might break the tooling, you're going to have a problem. So we don't want the inside bend radius to be less than 0.90. And maybe we don't even want it to be 0.90, or maybe we can't. I mean, determining what that value is, there's other things that factor in there. A lot of times it's based on what tooling you have in-house. So we're going to say in-house we have tooling to bend this at 1/8 of an inch. So I'll make that 0.125, and we'll hit the green check mark. And now we've got a sheet metal design that we can flatten. This was how we did it in the old days. Okay? If we wanted to create additional tabs, we would roll the tree back. We would create another feature here. We would create this feature again at 90 thou. So we would go to extrude and make that 0.090. And then when we roll forward, we would see that that becomes part of the sheet metal design. This can all be flattened. You can see we can click the flatten command. It all becomes flattened. And if for some reason we missed that number, if let's say we make that, I'm going to make it 0.1 instead of 0.090, we're going to have problems. So you can see here, we got an error, and we can see over here that that flange did not complete successfully. So you must have uniform wall thickness if you're going to use this command. The other thing that's important to know about sheet metal, and this exists all throughout sheet metal, is that the length of all of the edges combined will be different from the length in the flat. So in Solidworks, maybe you knew this, hopefully you knew this. If you didn't, now you do. If you click on something, you can often look down here and see what the measurement of that something is. Anybody not know about that? Show of hands. A couple people? I see you guys, yeah. Okay, cool, good. All right, so this is really helpful. It saves you going into the measure command over and over again, right? So we can also do that with multiple selections. I can do select tangency here, and I can see that the length of this edge here is about, we'll call it 8.4. Okay, 8.387. And if I do the same thing here on this edge, if I do a right mouse button select tangency, we can see the length of this is about 8.67. So 8.4, 8.67. But if I go into a flat pattern, the length of this edge is not 8.4 or 8.67, but instead is 8.528. So this is a function of what we call in sheet metal bend deformation or material deformation. And it basically means that when you're doing a bend in sheet metal, this region here is compressing slightly, and this region here is expanding. And so your flat pattern length is not going to be the same as the sum of all the edges in the form state. Now, this might not sound like a big deal, but if you think about it, our goal is to have a set of measurements here. We want this thing to be 5 inches long total. We want it to be 2 inches high total. If we didn't do that calculation correctly, we wouldn't establish that goal. We'd make bad parts. So when this came out in 1997, 1998, it was huge, right? It was so useful for SolidWorks users, and it saved us so much time. It's also just important to know that that is another fundamental of sheet metal for those of you in the room that maybe are a little newer. The other thing I want to mention about sheet metal in this older command, why are you telling me about this older command, is that there's still a really good use for it, and that is when you're working with imported models. So we talked a moment ago about bend deformation, right? This length, they're not going to be the same as the flat length. But let's talk a little bit about imported geometry, and shout out to Jacob Halassa. Is Jacob in the room? All right, well, shout out to Jacob for posting this file for me. It's a table, a really simple table here with a couple of shelves. And one of the shelves was created with sharp edges, and one of the shelves was created with round edges. But regardless of whether you're working with an import that your customer sends you that is already sharpened, or whether you're working with an import that is flattened, you still have the ability to open this in SolidWorks and turn it into sheet metal. And this is a spot where you can still use it to this day, and you still may find yourself using it. You can see here I can open up this model, which is a step file. It has no history tree. It's not a SolidWorks, native SolidWorks file. It's an import. I can choose this face. I can choose insert bends. I can choose what I want the bend radius to be, right? So now I need to figure out what the wall thickness is. So I'll pick this edge here, and I'll see that 3 millimeters, okay? So we'll go insert bends. Let's make that 4 millimeters. And now we have a sheet metal part that we can flatten. Pretty cool? Pretty cool? All right, cool. So for those of you that are taking notes, this is what my notes would look like. The insert bends command is more of an old school tool, circa 1997, 1998. It must have uniform wall thickness. The flat pattern length is different from the form length, but it can still be very useful, especially when you're working with imported models. Any questions so far? No questions, all right. That's what we call 100% comprehension. That means you guys are amazing students. All right, let's move on now and talk about the next section of our presentation, the second method of the 3 most common methods of creating sheet metal, the base flange and friends command. So this method is a little different. In the previous example, we would start out with a completed model. The model would be all uniform wall thickness, and then we would go in and insert bends. But with this method, what we do is we actually start out with a thin feature sketch. This is the more common, this was added in 2001, more common way of doing sheet metal today. If somebody gave me a print or a hand sketch and they said, hey, can you make this a bracket in SolidWorks? This is how I would do it. I would do it with base flange and friends. Definitely the most popular of the methods, but not the coolest. You might be surprised when I show you the third method, which I think is the coolest. After you're done creating that thin feature sketch, you're going to go into the base flange tab command, and then you're going to extrude this as a thin feature. You can see the UI looks very similar to a thin feature command, but during that extrusion, you're actually going to specify the wall thickness and the default bend radius. Then at the end, you're going to be able to create all these really cool additional features. So let's take a look at a quick example of this guy, the insert base flange command. We'll use the same technique we used last time. We'll start out on the front plane, begin a sketch, jump into the rectangle command, come across here. Let's say we make this 2 inches by 5 inches. Let's make another rectangle. We'll make this guy, say, 0.75 by 2. We'll jump into the trim command. Let's trim this up. Okay, sketch is underdefined, but that doesn't matter, right? Just leave it underdefined. No, never leave it underdefined. So we'll right mouse button, fully defined sketch, and we'll finish that off with some dimensions. And then we're going to take this top line here and turn it into for construction. Now we're going to go to the sheet metal tool, base flange tab. Once I go into the sheet metal base flange tab command, you can see that I'm immediately being asked to do essentially a thin feature extrusion. But the sheet metal features are already there, ready to go. This is the most popular, the most common way of doing sheet metal today. You can see here that I've got a field for what the default wall thickness is and a reverse direction. right? So basically what that reverse direction is saying is, what are you using this for? Is this supposed to be 2 inches from the floor to the top of the bracket? Or is this a bracket that's maybe holding a PC board that's 2 inches tall, right? Because if that's the case, this isn't going to work the way that it is now. So I would do a reverse direction so that it can enclose that geometry. I'm going to make this wall thickness 0.90, and just like we talked about before, I'm going to say that I want this to be 0.125. Now, sometimes people come at you with a little curveball, right? You go to work at a new company, and the guy says, you say, hey, what should the wall thickness be for that? And then he says, make it 12 gauge, right? And then you're like, oh, do I just type that in? Or how do I make it 12 gauge? I don't know what that's supposed to be. And so you have to go to some kind of a table, and you have to look it up, right? Well, what we have in SolidWorks is a really handy tool for that called a sheet metal gauge table. So this is a sample sheet metal gauge table just right out of the box. You can see that this is using the 3D Experience platform. No, I'm just kidding. This is Excel. So this is an Excel spreadsheet here. And in this Excel spreadsheet, you create your own columns. So you can modify these columns to make them whatever you want, right? So you make the gauge and the thickness match up appropriately for the type of material that you're using. You set the units to be what you want for the units. And then here what you can do is you can set these to be kind of dummy-proofed, so someone doesn't give the sheet metal a radius that's too small for the material. But you can also set them to only be available tooling that you have in-house. So that way you're ensured, you're guaranteed that you're going to be able to build this in-house. Or at least it's a little more likely. Never guaranteed, right? So what we're going to do here is we're going to choose this gauge table that we're looking at here. We're going to choose to make this thing out of 12 gauge. We can see 12 gauge down here. And we'll see how that responds in the SolidWorks software. So when we go to do an extrusion of a base flange tab, we have this check mark here that says Use Gauge Table. And now I can go into this pull down and I can select this gauge table here. And now you see that what I've got is pull down menus. So I've got this pull down menu here where I can go in and say I want that to be 12 gauge. So the wall thickness, I don't even choose the wall thickness. I just choose it right from that pull down menu. Simple Excel spreadsheet. You can just make a copy of it, modify the copy so it works for your material or your operation. And then here you can see that I can pull down this menu and I can choose the available bend radii. Pretty cool, right? Question? So the question was, is there any convention for thicker materials than just what's listed there? So the answer to that is, you just would add that in here to the table. So if you're working with gauge, if you're not working with gauge, you could just call it 0.75 inches or 3/4 inches like this, and then that'll show up in the gauge table. I haven't tested it with an actual /E, but I'm sure it'll work, right? Sure. Toby, tell him Toby sent you. And then you just put in what the wall thickness is, and then you would do 1, 1.25, 1.5, whatever the available bend radii are. And then that's what's going to dictate or populate those pull down menus. Yep. I think it's worth mentioning that along that same note, when it comes to figuring out how much deformation is taking place, right, I mentioned earlier that the length of the model in the flat is not going to be the sum of all the edges and arcs, right? It's going to be different because of bend deformation. That calculation is not necessarily an easy calculation to lock down. It's going to be different depending on what type of material you're using, what the bend radius is, what the angle of the bend is, what the material thickness is. These things are all going to factor into that calculation. So for today, what I want you to know is that it is a thing. It does exist. We have some great tools to help you determine that calculation and to get it right. Out of the box, you use a really basic tool called K-factor, which is just a ratio. A lot of times if you do a third of the way into the material, so a K-factor of 0.3333, it'll get you pretty close. Okay? But there are scenarios and companies where that number really needs to be accurate. And when you mention larger, thicker materials, that calculation is going to be different. What's that? Grain direction, another great point. That can also affect bend deformation, grain direction, yeah. And there's a section in drawings where SolidWorks addresses grain direction, and that's pretty much the only section where we really talk about that. Getting into the weeds a little bit here, you'd actually probably have to do that as multi-body and then combine them some way on the end. Yeah, it's another good point. So a lot of things can factor into this bend deformation. And it also depends on how accurate you need to be. Okay, question over here. Tooling, right? Tooling is going to affect it. Yep. Yeah, I completely agree. I mean, I think that we could actually have an entire session on this topic, but it would probably be us three and like 2 other people, right? And we'd be having the time of our lives in a giant empty room like this. But it is a nuanced topic, like a lot of things in engineering, that you can get really deep into almost any area. And it's important to know, and hopefully your takeaway from this session is that bend deformation is a thing. Look out for it. All right, let's finish up by doing this extrusion here. So we got our gauge table, we got our wall thickness, we got our bend radius, we hit the green check mark. That's the base flange tab command. And once we finish the base flange tab command, there's all these other cool commands that we can use right off of this sheet metal. Now you'll notice in the tree here that we've got the first feature, the base flange, and the last feature. Now I'm going to create another feature. I'm going to create what's called edge flange. And when I create edge flange here, you're going to see that edge flange lands in between that last feature, flat pattern, and this first feature here, sheet metal. So when you do base flange, you kind of sandwich all your features in between these other features. If I was to come in here and do, let's say, a hem, so I'm going to take this edge here and perform a hem command, so nobody cuts themselves on that. There we go. You can see that that also lands here in the tree above flat pattern. So when you use the base flange and friends, everything that you add is going to be added in between that start and that finish feature. What that last feature is actually doing is it's actually unfolding all of these bends. It's flattening each of these bends. So one by one, each of these bends is being flattened. If we unsuppress that last feature, it takes us into the flat pattern. And if we wanted to, one by one here, we could suppress these. If we were maybe designing a progressive die, something like that, we could create configurations at each state and then use those different configurations to actually design the progressive die around each of those bends. Although it's most popular, that's all I really have to say about that one for now. There's lots of cool commands that you can use on top of base flange, like miter flange, jog, hem, edge flange. Lots of really cool tools that you can use in coordination with the base flange and friends. If I was taking notes, this is probably what I would put. This is a command that you would use when you're starting new parts. If somebody gives you a napkin sketch, somebody gives you a 2D print, this is probably the commands that I would use to turn that into sheet metal. For me, a lot of times it's just like I'm looking at something and I'm just going to draw it up in sheet metal. This is what I use. Good? Good? Good. All right. Let's move on now. How's our time doing? 20:45. We're a little off from that. I think we all know we were a little bit off for the start of this, but we're pretty close to that time check. We'll boogie just a little bit to make up some time. Here we go. The coolest of the 3 methods I'm going to show you today, convert to sheet metal. When we're working with sheet metal and we have complex angles that are coming together, it can be really difficult to work with the traditional base flange tab commands. And an example of that can be seen here. If I open up this model, which has a 2D sketch that exists at a slight angle, you can see this angle here, and it's supposed to have a flange that comes up off of it and that flares out. So I'm going to select that 2D sketch and choose base flange tab. Now, because it's a closed sketch, instead of extruding as a thin feature, it basically just gives me a platform. So there it is, basic platform there. Now I'm going to select the edge of that geometry, and I'm going to choose to extend an edge flange. If I look at this thing from a side view, you can see that I can adjust the angle of this edge flange. There are some little tricks that we can use to dictate what that angle is, but unfortunately, one of those tricks is not to select my sketch layout. So I have to come up with some kind of workaround. Similarly, getting the height of all my flanges to be the same as this top plane here, there's not necessarily an automated way to do that. I probably, honestly, would just create them all and then just do a cut extrude using normal cut and cut them off at the top, but there's not really a more elegant way to do that. And then I'm going to do my edge flange here, and I'm going to get rid of this vertical relationship and have this thing flare out a few degrees. All right, not too bad for that first one. Let's create another edge flange coming off of here. So we go edge flange, we bring this guy up, and we have the same kind of challenges. We have to adjust the angle of this flange to match up with the other flange. And again, there are some tools, like maybe make it parallel to a face. Maybe I could try to do that and pick this face, but the problem is if we look at this from a front view, it's not really parallel or perpendicular because it's going off at a compound angle. Okay, and the challenges continue, and I'm sure you could imagine that as we continue around this model, it's just going to get more and more challenging. With convert to sheet metal, we're able to address those challenges in a really elegant way. So what I've got here is I've got just a boss extrusion, just a single sketch extruded, no draft on that sketch. This model does flare out, so I am going to put some draft on this thing. So I'll go to my draft command, and I'll say that I want to apply 6 degrees of draft on this front face here. I'll say that I want to apply 8 degrees of draft on these 1, 2, 3, 4 side faces. And I'll say that I want there to be 10 degrees of draft on this final face on the back here. Okay, I think that looks pretty good. Finally, what I'm going to do is just make a sketch here, converting those faces at the top, and I'm going to bring that up to surface to come up to this plane that I've created that represents the top of my model. And then the bottom of this thing also has an angle to it, so I'm going to pick this open 2D sketch and choose cut extrude, and then I'm going to say through all in both directions. And when you do that with an open sketch, it's the same as doing a cut with surface. So it just cuts the bottom of that model off. Looking at this thing from a side view, it looks like this. It's flared out in all directions. Let's talk about convert to sheet metal and how we can create this model, this vertical conveyor feeder, using convert to sheet metal in less than 5 minutes. Think we can do it? Yeah, we can do it, for sure. With convert to sheet metal, you start out with a solid. So you don't start out with surfaces, but you don't start out with a thin-walled model either. You click convert to sheet metal, and then you go around and you select, first of all, a face at the bottom of the model. It doesn't always have to be the bottom, but for today's example. A face at the bottom of the model, which represents our foundational face, and then edges where we want bends to take place. It doesn't care what the existing wall thickness is. We're going to input the wall thickness. We're going to input the bend radius. And this is going to leave us with a sheet metal design that we can then create additional features on, like base flanges, hems, edges, miters, all the cool sheet metal tools that we have. So here's what this design is going to look like, or what this process is going to look like. We go to the command, convert to sheet metal. It's here, computer, magnify. It's here on the sheet metal toolbar. Convert to sheet metal. Computer, demagnify. So we're going to click on that command, and then we're going to go to this lower face here, and SolidWorks is going to immediately apply a wall thickness to that lower face. I'm zooming way in here. It's kind of hard to see, but it has turned that lower face into a sheet metal design. Now, I'm going to say I want the wall thickness to be 0.125, the bend radius to be 0.25, and I'm going to pick this edge right here. And SolidWorks is going to eliminate the rest of the model and just leave me with that foundational face and then the edge that I selected for a bend in a sheet metal format. So with just a few additional clicks in the definition of that feature, I'm going to say, from the foundation, I also want to bend up this side and bend up this side. See what that looks like. Well, this thing's looking pretty good in just a couple of clicks, right? I'm going to say that I want to bend up this side over here, bend up this side, and then at the top, I want to bend up to that little straight region, bend up to that little straight region, that little straight region, that little straight region, and finally up to here. I never told SolidWorks to bend this edge here, so that remaining non-connected geometry is just eliminated. Is that so cool? And now, of course, from here, we can go to the edge flange command. Let's say we want to make an edge flange off of this edge here. We want it to be 2 inches, and we can actually pick multiple edges here. Pretty awesome, right? What about changes? We have to make changes. That's always the thing with SolidWorks, is that when you're working with SolidWorks and you need to make changes, it's going to happen, right? That's like what our strength is. So let's say we change this to 48, no problem. The whole thing just updates. Our sheet metal flat pattern updates. Everything's fine. It's just a solid. So cool. What do you guys think? Good? Yeah? Cool? Yeah, cool. Yes, let's clap for this feature and the R&D team that made it. Yeah, it is awesome, man. I've used it so many times to get me out of jams, and it's so easy to use. When you got complex geometry coming together, it's so easy to use. But it actually gets even better than that, because this can be used for imported geometry when you have non-uniform wall thickness, because the command insert bends needs everything to be uniform. But this command, this sheet metal convert to sheet metal, it doesn't care about that. You know, if I go in here, I'm going to open up another step file, and this one has non-uniform wall thickness. So, you know, the guy who was making this didn't really think about They were exporting it, they didn't realize these were different. So if I use the traditional insert bends, this is going to error. Hey, there's the error in the tree there. And we lose that flange that's non-uniform wall thickness. But if I do convert to sheet metal, I click on this face, and then SolidWorks says, well, what do you want that face to be? Do you want it to be 4 millimeters? Do you want it to be 1 millimeter? Right? It doesn't care what the existing wall thickness is. It's creating that wall thickness based on the face itself. So if I make that 3, and then I say I want this to be, say, 4 millimeters, and I pick this edge here, and I pick this edge here, SolidWorks is able to take that imported geometry that you got from your customer and turn it into something that you can flatten. The import tool also lets you create a multi-body sheet metal design. Or I'm sorry, not the import tool, sorry. The convert to sheet metal also lets you create a multi-body sheet metal design. So let's say we had a design like this vertical conveyor feeder, this hopper, and we want to turn this into sheet metal. How do we do it? Start with base flange tab? Nope. We're going to start with a solid, and we're going to turn that solid into sheet metal by using this option for keep body. So you remember that when I was showing you that first example of the hopper, the first thing I did was I just picked the bottom face and the first bend, and then I hit the check mark, and the rest of the solid body was discarded. Well, in this example, I'm going to keep that solid body, and I'm going to keep building off of that solid body to create multiple bodies in one part. So here's our solid, just regular old plain Jane features here. Convert to sheet metal. I want this to be my foundation. I want this edge to be bent, this edge to be bent, this edge to be bent, and this edge to be bent. And when I choose that and I hit the green check mark, oh wait, I misclicked, sorry. Try it again. Foundation. I clicked through and picked that back edge, that's what happened. Oh, stupid, God. All right, here we go. We're going to do this guy and this guy. And did I do it again? No. My bend radius was too small, and I was getting a problem with the gapping. So we go to the green check mark here, and you can see we discarded the solid body, which just leaves us with this sheet metal single body. But this time, I'm going to edit that feature, and I'm going to say keep that original solid body. So now I've got a sheet metal body right on top of my solid body. So now I'm going to perform convert to sheet metal again and say I want to use this face as my foundation, this edge to be bent, this edge to be bent, and I'm going to pick this, this face here to also be part of this bend process. SolidWorks is going to turn that region into sheet metal. And then finally, I'm going to choose to create a sheet metal design in this top region by saying this is my, what I call foundational face. And this edge should be bent down. I'm going to bend over to this edge, down to this edge here, over to this edge, down to this edge here, over to this edge, and down to this edge here. And SolidWorks is going to automatically rip that final edge. And this time I'm going to say I'm done with that original solid body, remove that final solid body, and you can see that I'm left with this multi-body solid where any one of these bodies I can click on and jump into a flat pattern view. And if you've ever worked with multi-body, you'll know that, of course, we could take all of those views and put them onto the same drawing. We could even create an exploded view of the multi-body and create a bill of materials from that multi-body design. So convert to sheet metal is awesome. Like I said, I think it's probably the coolest of the three. You start with a solid, and then you go to the sheet metal conversion process. When you're done, you can create additional features like the edge flange, miter flange, hem, all those cool features. It's great for complex angled parts. It's great for multi-body design. And it can be used for imports even if they have non-uniform wall thickness. And just like all of our examples today, the flat pattern length will be a little bit different from the form length. Pretty cool. Any questions? Question? So the question is, to do a cone, a flatten a cone, is the best way to do it using insert bends? Probably. I mean, I'd have to see the geometry. It kind of depends on what's downstream. I'd consider that a fringe case, ultimately. I think that's going to be my answer. So for example, I could do that with surface. I could create it as surfaces and then do flattened surface and examine the deformation and see if that's going to get me close enough for manufacturing. I think that you can do it with a loft if you are careful about how you design your profiles. We have a lofted sheet metal command. So I'd have to see, but I mean, yeah, I'd consider it a little bit fringe and something that maybe is marginal. If it was at a glance, if someone said, how do you do a cone? That's how I would do it. Design it as a solid, insert bends. And then you pick the edge, right? Instead of picking a flat face, you pick the edge. Yeah. Great question. Question? Yeah, so another question was, there's a feature called collect all bends, really handy feature. If there's any existing tangency when you go to do convert to sheet metal, you can automatically grab all that existing tangency in one shot. Yep, a nice shortcut when you're in there. Okay, we're gonna move on here to the next section, which is talking about flat patterns in sheet metal. And when it comes to flat patterns in sheet metal, there are some things that are important to know, some options you can look at, but the most important thing is, how do you make a flat pattern configuration in sheet metal? So how do we get to this point? Does anybody want to guess, or does anybody know? How do you make this configuration? If you know, just hold off a second. Don't answer right away. Okay, now you can answer if you know. How do you get to this point? What's the answer? Start a drawing. That's the right answer. Believe it or not, that is the correct answer. You start a drawing. When you go to create a new drawing in Solidworks, this new configuration will be automatically created. It is a derived configuration, and it has a very specific naming convention. If you don't match that derived configuration naming convention, you're not going to get all the cool functionality that you can get from sheet metal. So if I have this part here, and this part has one single configuration, and I go to File, Make Drawing from Part, we can see that as soon as I start a new drawing and select a sheet format, this new drawing will generate this area over here on the right called the drawing preview pane, and one of those previews has the geometry in a different state. In order for the geometry to be in a different state, a new configuration had to be created. So even if I begin a drawing and immediately cancel it, this new configuration has been created. A lot of times when I want to make a flat pattern, I'll just do that. I'll make a new drawing and then insta-cancel it, just because I don't want to go through the process of making a derived configuration and naming it default SM flat pattern. So that's the answer to how do I make a sheet metal flat pattern configuration. Just kick off a new drawing and let the software make it for you. It will name it correctly based on whatever the currently active configuration is. Now, if we go into drawing mode here, so if I go File, Make Assembly from Part, nope, Drawing from Part, and then I go to the flat pattern configuration, it looks really good. You know, a lot of times what I'll do when I'm making a drawing of a sheet metal part is I'll start out on the first sheet. I'm sure a lot of you have done this before. And we'll go through the first sheet and we'll add in our appropriate views here, set our scale appropriately, and then we'll add a second sheet. And a little trick that I like to use on the second sheet is I delete the sheet format from the tree. So you go here to the second sheet and you're going to export this to the Amada or to the whatever you're cutting it with, the laser cutter or water jet. And then I'll go here and I'll say delete. So I'm doing a right mouse button in the tree and I'm deleting the sheet format so that the second sheet is totally blank. And then that's where I'm going to add my flat pattern view. Pretty cool, right? You guys knew about that? Yeah, some of you, yeah. Okay. I can click on this view here and there's a section that's dedicated to flat pattern display where I can change the rotation. I can even pick it up and flip it on the drawing. So maybe I'll change this to 90 degrees and you can see what it looks like. If the burrs are going the wrong way, if you're doing like a punching operation, you're going to get burrs on the edges where you punch through. If you want them to go the other way, you could pick up the whole thing and flip it over and then send it to the machine in that orientation. You can do that using this flip view thing here. But check this out. I'm going to go back into my original model and I'm going to say add configuration and I'll call this Toby flat. And I'll go to my feature tree and I'll suppress the flat pattern or unsuppress the flat pattern. That looks beautiful. I got myself a really nice flat pattern there, right? And now I'm going to insert a model view of that model in the top view. Okay, that looks pretty good. And it's oriented the wrong way, right? So I'm going to click on the view and come over here to where it says flat pattern and change the angle. Wait, this one, flat pattern display. This one, no flat pattern display. right? So the drawing actually doesn't recognize this as a flat pattern because it's not a derived configuration and named the correct way. So this is just another example of where you may miss out on some sheet metal functionality, and if you want to avoid that, just let the software create the configuration for you. Cool? Cool? Okay, cool. Let's talk about a couple more things. Let's talk about these corners. What do we think about these corners? Do these look good? Maybe not, right? What should they look like? What do you guys think? What should they look like? Right? In the form view, it looks like this. The flat view, it looks like this. What's going on there? Right? So what's happening here is that when you have a sheet metal design, you're going to have a section at the bottom of the tree called flat pattern, a feature called flat pattern. And when we go to that feature called flat pattern and we say edit feature, there's going to be some options here. And one of those options is called corner treatment. This is a little bit of a legacy option. It's basically saying that after you create the flat, you're going to come in here and you're going to punch in some features, maybe just using a straight punch or a hole type command. And that's going to create some clearance for your bends, some relief for your bends. It's going to make it easier to do the bending process. But I don't personally like this because it's not the same as what you're going to ultimately get in the formed view. Right now, my formed view looks one way and my flattened view looks a different way. The customer might be expecting to get this and then end up getting something that has these holes punched in it. Right? So instead, I would go about this a different way. And what I really want is I don't want to use the option for corner treatment. I want whatever's in the form view to look like the flat view. So I'm going to say edit feature, and I'm going to uncheck this option for corner treatment. This is one of the most common things that people ask me about in sheet metal and in tech support. So it's a good one to look out for. You edit the flat pattern, and you uncheck this option for corner treatment. Uncheck that option, and you're going to get, the behavior that you're expecting, the geometry that you're expecting. There's a couple other options in there that are good to know about. I mean, probably the other big one would be merge faces. Really straightforward. Merge faces, the whole thing ends up being one single face. Your machining software might prefer this. If you don't have merge faces turned on, then when you go into the flat pattern, each bent face is going to kind of retain its face ID. Makes sense, right? Pretty straightforward. The other ones that are in there are for a little bit more nuanced, a little bit more fringe cases, so we don't have to get too into them right now. So just a little bit there about the flat pattern options. To edit those options, you go to the bottom of the tree, right mouse button on flat pattern, and you can choose edit feature. We also got to have a quick discussion about display states. So the difference between display states and configurations can be summed up very simply by saying configurations are a change to geometry. Display states are a change to appearance. If you've got an assembly, you could have one version of the assembly where two of the parts are hidden and another version where they're shown. Does that need to be a new configuration? Does that need to be taking up additional resources on your machine, both in hard storage and in RAM, having multiple configurations? No, it could just be a display state. So display states were created to help with that challenge of, look, all I want to do is hide a couple of these parts or change the way some of these parts are colored. I don't want to have to make a whole new configuration just for that. But when it comes to sheet metal and part management in general, it's pretty common that you can end up doing what's called a linked display state command. So here in the properties of a display state, you could say, I want to link my display state to the configuration, which means that the flat pattern has a display state called to, and the default has a display state called default. And so if we are working in Solidworks and we are examining our flat pattern, and we decide, hey, I want this to be a little bit of a different color. I just want it to be a slightly different color. Maybe make it a little bit more. Okay. Oh yeah, that looks great. That's going to look great for everything. Then you go back to your form view, and in your form view, it ends up looking a little different, right? So you've got your, sorry, I didn't change configurations. What am I doing? I'm going nuts. Here we go. It's linked to the configuration. There we go. Has anybody ever run into this? I know this is a pretty common thing. Okay, I see a couple of hands. Yeah, so this is what's happening. And the way you resolve this is you just get down here into your display states and you say properties, one single display state. One single display state. Don't link the display states. I just want one. One ring to rule them all, right? One to bind them. So we'll get rid of these other display states. And now, as we click around, we always stay in that one single display state. You're not going to get that different appearance for the different configurations. Because it's linked, right? All right, and then the final thing I want to tell you about with regards to multi-body sheet metal is that in general, when you're working in SolidWorks, you've got the ability to have a multi-body design and to just select one body from that multi-body design to bring into a drawing. So for example, if I use this, I'll use this weldment, which is a really common example of multi-body, just mixing it up a little because we've been doing sheet metal for so long. If I use this weldment as an example, and I bring in the weldment in its isometric view, maybe I want to create a weldment table, so I'll go here to Tables, Weldment Table, and then I'm going to create an auto balloon. I'm going to auto balloon this thing so that we've got all of our balloons for this. We can do this exact same thing with sheet metal. I'm just mixing it up a little bit here. What I can do is I can then go to Drawing Model View, select the name of that part, and then in this second window here for Model View, choose Select Bodies. And once I choose Select Bodies, the part model opens, and I can pick one or more bodies to create an explicit view of just that body. So now I can get in here and tell the manufacturing team that this needs to be cut at an unusual angle. Pretty cool, right? So this is the same way you would do it with sheet metal. When you're working with sheet metal, you would do the exact same thing. You would create a drawing, and you would say, I want to create a model view. I'm going to select this one single body, and then when you go to bring in that model view, you'll see that there'll be an option for flat pattern for that model view. So we're at 45 minutes, which puts us almost at 2:30. I know we're winding down on this session, but I did want to give the audience a chance to ask some questions. So if there are any questions out there, I'm happy to take those questions. Looks like we have a question over here. Oh, it's Kurt. Hey, everybody, this is Kurt.
Hi, Toby.
Oh, a SolidWorks question.
Sorry.
Whoa, mic'd up, huh?
Yeah. Do you think the audience would like to take a sneak peek at a preview of what's coming soon in SolidWorks?
Oh, do you have access to such things?
I might have access.
Wow, what do you guys think? You guys think you might want to see some more sheet metal stuff coming?
We
All right.
promised that we were doing this this morning in the general session on the side stage. So I'm thrilled to come up here and give you a quick preview of what's coming really soon in SolidWorks for sheet metal.
Whoa.
So, by the way, if you miss any of this, it's all being recorded on SolidWorks Live, live.solidworks.com. You can find it on Facebook and YouTube and all that as well. And if you want to tell your friends, hashtag SWLive, okay? They can all go back and watch it later as well.
Nice.
Should we get started?
Yeah, let's do it.
All right. Go ahead.
All right.
Go ahead. So I think everybody agrees that sheet metal is a pretty powerful and cost-effective design technique, right? And for a long time, we've had really powerful tools, like pulling an edge flange off of a fairly complex base flange like this. Just select along the tangent edges, and I can pull that out. Pretty simple, right? We've also used multi-body techniques. We've talked about swept flange. We have all of this amazing functionality to do pretty complex sheet metal designs, but what we've never been able to do is pull an edge flange off of a tangent set of curved edges that are in 3D. So coming soon in SolidWorks, you'll be able to create an edge flange off the tangent edges of non-planar edge flanges or base flanges. Or yes.
Whoa,
so
that
what
is
you're seeing
cool.
here is exactly that. I can pull those off of a swept flange or a base flange. I can pull them off of an existing edge flange like you see here. And again, this is a multi-body approach to get that type of a result. Now, obviously, it's a pretty complex sheet metal flat pattern. What do you think? The command wouldn't be complete, Toby, if we couldn't flatten the design, right? So
yeah.
Of course, right there it is. Just like Toby showed you earlier, I hit flatten, and there's the flat pattern of my design. Everything done. So this is coming soon. This is under development. If you know about the beta program, you can play with it there in the beta program. Might be around in here as well, but that's some new stuff coming. We're going to drop in on a few more sessions throughout the course of the event, so stay tuned. If you miss any of them, they are on SolidWorks Live, live.solidworks.com. Check us out. Thank you very much.
Oh, that is awesome. Thank
Toby,
you, Kurt. Yeah,
great presentation.
That's awesome, yeah.